Okay, so we're gonna just finish up where we left off in 12.1 and then jump into 12.2. So this is right here. This is an equation of a sphere, and we just need to complete the square to. So what we're going to do is complete the square to find the center and the radius. So what do we get? We get x squared minus 4x plus 4 minus 4. And then in y we have 10y plus 25 minus 25 plus z squared is equal to 2. So we end up with x minus 2 squared plus y plus 5 squared is equal to, oops, forgot about the z squared here, plus z squared is equal to 31. And so our center here is 2, negative 5, 0. And the radius is the square root of 31. Okay, so this is one type of problem. The other problem I left off with was defining this region with x squared plus y squared plus z squared between 1 and 16. So what is this? Well, we essentially have two defining boundary equations. This equals 1 and whoops, and this equaling 16. So here we have a center 0. We're just going to use 0 hat for which is 0, 0, 0. And R is 1. It's the same center here, centered at the origin. R is 4 here. So it's between the sphere of radius 1 and the sphere of radius 4. Let's just draw this region. So we have one sphere here, center, this is radius 1. And then we go out to radius 4 here, get a much larger sphere. And it's kind of the inside has been removed. It's almost like a, reminds me of Ferrero Rocher chocolate, but anyhow, something like that. Let me just use a color to kind of shade what actually is being talked about here. So it's everything outside of the sphere, and it's including the boundary. It's outside of the sphere of radius 1, including the edges, and inside of the sphere of radius 4. So it's kind of a cool region. Okay, you can make all sorts of upgrades on these kinds of things, but that essentially was the exercises from last time. Now it's going to jump into 12.2, which is all about vectors. So what is a vector? It's probably best just seen by an example, but let's just define it. A vector is a mathematical, we'll call it an expression that has both direction and magnitude. Reminds me a bit of Despicable Me, but anyhow, it's kind of a fun reference. And it's usually denoted by an arrow, something like this, and either by an arrow, and then usually you have some letter V with a little vector, kind of mini vector on top, where that V corresponds to this guy, to this particular arrow. So you can actually think of vectors completely coordinate free. So for example, if you had a vector U here and a vector V here, their sum, if you added them up, you would get this vector, U plus V. You can also multiply, so vectors can be multiplied. I'm doing this discussion a bit informally. If you do something like linear algebra, you can get a much more formal definition of vectors and what's called a vector space and so on. I'm doing it a bit informally here. Vectors can be multiplied by scalar quantities, scalars, which are essentially some numbers from what's called a field. In this case, it's just the real numbers. Numbers, in this case, the real numbers. So for example, suppose I wanted to find out if I'm given U and V, what does U minus V look like? Oops. U minus V look like? Well, if here's U, well, positive V was up here, then let me adjust this drawing just a tad here. So here's U, then negative V will be in the opposite direction, the same magnitude. And by the parallelogram, or this is called the Parallelogram Law, by how to add vectors, using that same idea, if you're adding U and minus V, you would end up with this vector. Put it in another way, more commonly, if you had U like so, and you place V here with the same base point, so it's V, U minus V is right here. It goes U minus V. So it's the same here as U minus V. Okay, so this is kind of a little bit about vectors in abstract. Generally speaking, we use coordinates. So let's start off with the vectors in R2. We'll move to R3 pretty shortly. It's very similar type deals. So for example, let's just check that everything we've been drawing in abstract actually makes sense. So let's say U is 2, 1. V is 2, 5. What is U plus V? Well, U plus V is simply add coordinate-wise. You get 2 plus 2, comma 1 plus 5. Is 4, 6. So let's just draw that. So we have 1, 2, and then 1. And then let's say the U starts at 0, 0 and goes to 2, 1. And remember, these vectors can kind of be moved. So let's say this V starts just to match it up with our picture, let's say this starts at the point A equals 2, 1. So from 2, 1, which is the tip of the u vector, we go 2 units to the right. So 1, 2, which is up to the 4 mark, and then 5 units up. 1, 2, 3. Just that a little better. 1, 2, 3. Sorry, 1, 2, 3, 4, and 5. So this gets you up to the 6 mark here. And you're going to start here and end at this point 4, 6. That would be u. And you can see that u plus v actually is the vector starting at the origin. That's u plus v, which exactly corresponds to that. Okay. What else do we want here? Well, let's look at u minus v. So now let's go ahead and see. Let's do this first purely. So here's u. V is 2, 5. So 2, 1, 3, 4, and 5. So we have this vector 2, 5. So it's v. So it's u down here. And let's take the vector, just draw from the tip of this guy to this. This should be u minus v. And indeed, if you take 2, 1, and you subtract 2, 5, what do you get? You get the vector 0, minus 4. And this vector corresponds, if we had to draw 0, minus 4 from the origin, we would have 0, minus 4, something like this, and that vector is exactly the same as that. So vectors can be what's called translated. Vectors can be translated to start at any base point. At any base point you like. Base point. Okay. All right. So these are some basic examples that are good to keep in mind. A little point to note here. So the vector going from a point A, and let's now, I'm just going to jump here to 3 dimensions, x naught, y naught, z naught, to the point B, which is x1, y1, z1. How do you write that? So that'll be A, B, the little dash. That's what's so denoted by. Well, it's just this point B minus this point A. So it's x1 minus x0, y1 minus y0, z1 minus z0. Okay, so for example, if you had to go from the point 1, 1, 2 to the point 2, 3, negative 1, then what would that vector look like? It would be, oops, two minus 1, 3 minus 1, negative 1 minus 2, which is 1, 2, negative 3. Okay, so that's a good thing to note. All of these vectors can be multiplied by scalars. So for example, if v was the vector 1, 1, 1, So let's just draw a couple of vectors in 3 dimensions, at least try. So here's 1, here's 1, here's 1. So I'm going to think of, by default, I'm thinking of vectors starting at the origin and then going up to this point. So this would be the vector, this would be v. If I multiplied v by 2, just multiply each component by 2, which is 2 times 1, 1, 1. How would that look like? Well, it would just stretch. You would stretch beyond to 2, 2, and 2, so you would end up just stretching the vector a little further up. You'd go a little higher here. So let me draw that with still yet a different color. That would be this vector. So this would be 2v. So scalar multiplication stretches vectors either in the positive direction, or of course you can go in the negative direction. If you had negative v, you would be going to negative 1, negative 1, negative 1. It's by the way, where I think I did not mention this in an earlier video, which I should have in 12.1, but so the region where all our coordinates are positive, this is called the first octant. First octant. So right now, with all 3 being positive, we're in the first octant. But for this guy, this would not. And what's the second and the third? There's 8 octants, obviously, but the ordering, to be honest, gets a little mixed up. But this is sort of in the region where in the diagonal opposite. So this is the region opposite to the first octant. So you'd have to go kind of. I'm not going to be able to draw this very well, guys, but you'd have to go sort of diagonally back somehow to get to that region. So just something to keep in mind, that scalar multiplication can change the direction of the vector. So let me just write, at least in R2 it's straightforward, right? 1, 1 is right here, and then negative 1 should be angular brackets here. And this is negative 1, negative 1. Okay. All right. Let me just state a couple of more things here before we stop. There are sort of what are called the standard basis vectors. I, j, and k, where I is the vector 1, 0, 0, j is the vector 0, 1, 0, and k is the vector 0, 0, 1. And so any, why do they use this term basis? It's a term from linear algebra, but essentially it just means if I'm given any vector a, b, c, I can write this as a times the vector I plus b times the vector j plus c times the vector k. You can kind of see that relatively straightforwardly, and any vector can be decomposed like this into this what's called a linear combination of these 3 vectors. Turns out to be somewhat useful, and it's used quite often in the book. I will talk more about that probably at some other point. So just visually though, here's I, here's k, and here's j. It literally spans. So I is pointing in the x direction. This is the unit. It's called a unit vector. We'll talk about that in just a second. J is pointing in the y direction. and k is pointing in the z direction. Okay. Last but not least, before I conclude, I just want to talk about what's called unit vectors. So unit vectors are vectors of length 1. And so for example, first of all, what is the length of a vector? So we need to define, or well, it's not really a definition, it derives from the distance formula. So given a vector, say u equals u1, u2, u3, the length of u is denoted by this absolute value. This is the length of u, and it equals the square root of u1 squared plus u2 squared plus u3 squared. Okay. So I'll leave it as a little, it's a little bit trivial here, but I'll leave it as an exercise. You can see that the vectors I, j, and k are unit vectors. They have length 1. You don't even really need to use the distance formula. You can just see it visually. But what if you're given a general vector that's not a unit vector? Let's say you have 1, 2, negative 1, which has length the square root of 1 squared plus 2 squared plus negative 1 squared, which is the square root of 4 plus 2 is 6. How do we get it? What we want is to find a unit vector. Just for simplicity, just for clarity, let me call this v, and the unit vector, let's call this v. If you have a general vector v, 1, 2, negative 1, which has length 6, I want to find a unit vector u pointing in the same direction as v, but which has length 1. Well, I guess that's a redundancy. Find a unit vector pointing in the same direction as v. If it's a unit vector, then it has length 1, so I'm just not going to state that. So I'll leave this as a little exercise. We'll end right here. I'll do a little more on unit vectors in the next video. So exercise, compute the vector v divided by the length of v for this particular v, for v given above. And show that it actually has unit length. Show that v divided by the length of v, right? This is essentially 1 over the length of v multiplied by the vector v. So it's a scalar multiple of that. Show that this is a unit vector. All right, and I'll start with this exercise and do a little more on unit vectors in the next video.